Hi class. So today we're gonna be talking about K-nearest neighbor. So we're gonna do two parts of a video. The first part is just the PowerPoint to introduce you to what the K-nearest neighbor model means, and then we'll show you a Python K-neighbor nearest neighbor lecture. Okay, so on this first PowerPoint, you don't need to type anything. It's just for us to understand a little more on the theoretical part of the K-nearest neighbor. And then we'll do another section where I explained the application in Python. Okay, so on the other one, you would need to follow up with by downloading the application into your Colab. But for this one, you don't need to download anything. You can just open up the PowerPoint and follow along. All right. So this is the first video. And here is introduction to K-nearest neighbor. So K-nearest neighbor is another model that we can use to predict to do a prediction based on classification. So we're going to talk about what a classification is, introduction to the KNN, and evaluating classifiers. And in this case, it does have a hyperparameter tuning K. Not like the linear regression, but it didn't have any hyperparameters, so we didn't have to do any tuning. In this case, we do have a K value that will allow us to be able to optimize our classification. So what is the mean classification? So classification is a task of splitting or organizing data into different classes based on the features of the data. So what we're going to do is we're going to try to separate groups of data based on the data that we have. And then a class is one of those, is one of the categories that we assign to the data. The class is the label of the classification. So as we classify our data, each one will represent a class. A feature is one of the variables that classification uses to organize the data into different classes. Features are inputs of the classification. So in order to be able to determine in which class the data will follow along, we need some data about it, and those data that we're going to use to be able to classify them is called the features. And practically the features are practically the columns on the data. So here's an example. So we're going to be talking about classification. Again, classification is a task splitting or organizing the data into different classes based on the feature of the data. So here the features would be, for example, if we want to be able to identify or classify animals. And so we're going to be looking at the ears, the eyes, the tail, and the paw. So those are the features. Right? So those are the columns descriptions of what this that's going to help us to be able to classify our data into a cat. So we're going to take all these features, ears, eyes, tail, paw, we're going to put it into the classification algorithm, and it's going to classify them into the class of cat. So in this case, cat is one of those classes. So that's practically what classification means. So here's another example. So here, again, classification is the task of splitting or organizing the data into different classes based on the features of the data. So, for example, a doctor might want to classify a patient as either sick or healthy. So the class in this case is either sick or healthy. So the doctor's trying to classify into two different categories. These categories are the classes. So either is a class sick or healthy. Use information like if they have sore throat, or a fever. So that will be the features, right? So looking at the data that we get, we're gonna be able to classify them, put them into a class. Okay. There's different versions of the type of classification. For example, the binary classification. A binary classification organizes each instance of data into one of two possible categories. So in this case, there's only two possible classes. It's so in this case, So when we have binary classification, there's only two possible classes. It's either one or the other one. It's either a spam or not a spam. So that's what we call a binary classification. When we multiply a multi-class classification, organizes each instance of the data into one of three or more possible categories. So it has to be three or more classifications, because if it's only two, then that's a binary classification. So if it is more than two, in other words, three or more classes, then that's going to be considered a multi-class classification. So in this case, for example, we are determining what kind of animal it is based on the features. And so in this case, we have the options, the classes, the options to choose, to select or to predict that it's a dog, cat, horse, fish, or bird. So you can see here we have 5 different classes. And so this is called a multi-class classification. Now there's another one that is called a multi-level classification. A multi-level classification organizes each instance of the data into multiple categories of many options. So for in this case, we might have, for example, a picture that contains multiple animals. And in this case, we're going to be able to predict or determine the two items, the two animals that are in the picture. In this case, we have a cat and an eagle. Sorry, a bird. So in this case, we're doing a multi-level classification. So not only do we select we have multiple classes, dog, cat, horse, fish, and bird, but we're able to determine that there's more than 2 different labels. There's more than 2 different classes in the same picture. So this is successfully determining there's a cat in the picture and there's a bird in the picture. So that's what we call a multi-level classification, when the output will be cat and bird. So that's a multi-level classification. Right, so classification or not. So do you want to be, so here's an example or a few examples where we can play around to determine if it's a classification or not. Do you want to say what kind of shopper someone is based on their past purchases? So that'd be a multi-class classification. Do you want to predict when houses prices will be the lowest to buy? And that would be no, right? Because we talked about that. That's more continuous label or target. Do you want to predict whether a past customer will make another purchase? And that is a binary classification. It's either yes or no. You want to guess what the average temperature of a different place shown in the images is. So again, that temperature is continuous, so it's not a classification. Do you want to guess as much as possible about a place shown in each image, such as the country, and the season? So in this case, you have a picture where we have multiple things about that we can classify, right? In this case, that will be a multi-level classification. Remember that in supervised learning, the label determines the task. Remember that the label determines the task. In other words, your target column, that's your label, your target column, what you're trying to predict, right? In the end, will be what determines what kind of label determines what kind of task you have. So remember the label determines, the target determines what kind of task you have. So if the label is a class category, this is a classification. If the label is a continuous, then it is going to be a regression. Okay. So one model that helps us to be able to determine classification is called the k-nearest neighbors. So the k-nearest neighbors is a supervised learning algorithm that classifies new data points based on which training data points they're close to. A KNN assumes that the closer data points are more similar to each other. So what does this mean? It means that you know how they say that, you know, if you hang out with, you know, smart people, then you're like a smart person. If you hang out with athletes, you're more likely to be an athlete. So this is kind of like what they're saying. Is they're saying if you're near around this class, then you're more likely to be that type of class. So that's what this is saying. So and so that's the idea of the k nearest neighbor. So who is around you is going to determine who you are. So here's an example. So does the new data point below belong to the category A or category B, right? So we have this star point, and we want to determine, does it belong to category A or does it belong to category B? So we're going to say that because it is closer to the elements of category A than to the labels of category A, then it's going to be a type category A of class A. So that's the idea, is that whoever you're closer to on your neighbors, that's going to be who defines you. So here's an example of animal classification. So we have cats and cats, right? And now here it could be that we have this fish right here that is a little bit in the far side, and it's going to be wrongly determined that that is going to be a classification cat, right? So it should be really closer to the fish. So that's the disadvantage, that just because it is closer doesn't mean that it belongs to them. But that's the idea, is that it makes an assumption that if you are close to this group, then it's going to belong to that set, and that is to that class, and that's not always true, right? But that's just an example, right? Just to give you that it's not always perfect. Here's another way how it works. So how the KN works. So when we get the new data point, the model computes the distance to every training data point. So you can see here, we have this new point in the question mark. And what it's going to do is going to find the distance of that new point to every single point on the graph. So let me say that again. The new point, what it's going to do, the nearest neighbor, is going to find the distance to every single point on the graph. Okay, that's a lot of work if you have 1,000 different points. The model then looks at the classes of the k nearest training data points. Then the model takes a majority vote of these classes and returns the results as it is prediction. Okay, so remember that I said that when you introduce a new point and you want to determine to what class it belongs to, right, it's going to calculate the distance from that point to every single point on the graph. So it's going to check the distance of every single point. Now, what does it mean when you talk about the k nearest neighbor, right? What it's going to do is going to look at the k closest points. So let's say the k is equal to 3. If k is equal to 3, it's going to look at the k nearest, the shortest distance from that new point to the three closest to it. So just 3. In this case, if k is equal to 3, then it's going to only look to the 3 closest. Because remember, we check for all the distance of all the points. We're going to be able to find out the closest ones. That means the shortest distance from the new point. So as you can see here, we have the star and the 3 green triangles that are the closest to that new point. Based on those only 3 points, right, we're gonna, because we selected k to be 3, is going to determine by the majority vote. In this case, there's more green triangles than stars. So we're gonna label this new point as class B. And that's what the k nearest neighbors does. It first looks at all the distance from that new point to every single point on the graph. And then based on the value of k, it will look at the k nearest points and take a majority vote. Now, obviously, you want to make sure that your k is at least an odd number. Otherwise, you might get that we have, let's say we have a 4 and 4. So this is not going to be a majority vote, right? It's going to be, let's say we have 2 and 2. So So we have a size 4 K, and there's 2 elements that are star and 2 elements that are triangle. So we won't be able to determine in which class does it belong. But ideally, you always want to choose a K value that is odd. Finding your next favorite book. So here's another example of how you can interpret this. K is a hyperparameter that refers to how many of the nearest data points you will consider when classifying the new data point. So we use this K, right? We're gonna look at the K nearest neighbors, and sometimes, well, that K is what we call the hyperparameter, meaning that we can tune this value K, we can try different values of K and optimize our performance. So maybe if we take raise K to, instead of being 3 equals to 5, will give us a much better outcome, a prediction of classifying that label. So for example, you have finished your new book, a thrilling detective novel. So you go to the bookstore and want to choose which author to read next. You consider every book in the giant bookstore, each with a feature including gender, author, publication, year, and reader ratings. The bookstore organizes these books according to their similarities in the features. For example, a detective novel by the same author from the same era would be physically considered closer to your favorite book than a romantic novel from a different author. So that's just giving you a scenario. Finding your next favorite book, you choose K to be equal to 5. So you will look at 5 books in the store that are physically closest to the detective novel you're just finished. And the reason is because the library has set up your books in that form, right? The same books, the same author would be close to itself, right? So the author will be similar books will be near itself, and if it's not the same author, the same type of stories or same type of genre or type of stories will be near that area. So suppose 3 of these 5 books are by the same author and 2 are by a different author in the same genre. Since the majority of 3 to 5 of the nearest neighbors are from the same author, you decide to read another book by the same from this author. So that's kind of like the idea of K nearest neighbor. Now, how do we do this? How do we determine which points are the closest, right? So what we do is we use the Euclidean distance to be able to find the distance between any point. So if we're talking about two-dimensional space, we could use the Euclidean distance formula, which is the square root of the difference of x plus the square root of the difference of y. And that will give you the distance from one point to another point. And if so we would do it for every single point, like I said, in your graph. Now that could be a lot of work if you have 1,000 different points. And so the reason we need to do this is because we need to find the points that are closest, the k points that are closest to the star, to the new point. If we're talking about instead of a 2-dimensional, but a 3-dimensional or a 4th-dimensional or a 5th-dimension, it doesn't make any difference. We'll apply the same formula, and the formula will be a much more multi-dimensional Euclidean distance formula. So what we do, we take the difference in feature one, the difference in feature one difference from 2 points, plus so we take the square root of feature 1 difference square plus feature 2 difference square plus feature 3 difference square, and so on until you have completed all the features that helps you classify your label. So you can see here the example with a 3-dimensional space or the 2-dimensional space, but we can take it to a 4th dimension, 5th dimension, and 6th dimension, depending on how many features you have. The features determine the number of features will determine how many, in what dimensions you're gonna do this Euclidean difference. What is the pros and cons of a KNN? Easy to implement, no need to train a model, versatile, can be used for classification, regression, and search, but it's typically used for classification. What is the cons? It does not scale well. Why? Because let's say you go from 1,000 to a million. Imagine you have to do the difference. You have to find the distance of a million different points from the new point that you're trying to predict. It's a curse of dimensionality, so you can have multiple dimensions. So imagine that you not only have a million different points, but you have, let's say, 10,000 different features, right? And then it's too many dimensions to be able to do that difference. Is prone to overfitting, not suitable for large data sets or fast predictions. KNN is a lazy algorithm. It's called lazy algorithm because it has to do a lot of operations. KNN is considered a lazy algorithm. It's not ideal for handling large data sets or fast predictions. KNN stores the entire training data set and does not build a model during the training phase like eager learning algorithm. So it's not actually learning from itself, right? This prediction model. So it's not learning from itself. So every single time you add a new point, it's going to have to do the distance formula. During predictions, KNN must compare the new data point to all the training data points. So you have to do the comparison. The new point has to be compared to every single point on the data training, which can be too much work, which can be almost computational expensive. How do we evaluate classifiers, right? Accuracy. The most straightforward way to evaluate our model is to determine how accurate it is. In other words, what fraction of the model's predictions were correct. Accuracy. So the accuracy will be measured by the number of correct predictions. So that will be the predictions where the label was guessed correctly to be true, and when it's guessed to be correctly wrong, right? So that's gonna be the two possible options. So the formula for accuracy can be broken down as given below. We will now explore this new term. So accuracy will be the number of true positives plus the number of true negatives divided by the number of predictions total. So it's a very straightforward formula. So the accuracy would be the total number of correct predictions. So that will be the number of true positives plus the number of true negatives. So that's when we, for example, we would choose, we predicted that it's a cat and it is a cat. And so that will be a true positive. Or when we choose we determine that it's not a cat, and the answer is correct, that it's not a cat. So that will be a true negative. We'll explain a little more of that. So definitions on true positive. It's a classification prediction that correctly classifies a data point in one class, which we'll call the positive class. So we positively successfully determine that the class is true. It is the right answer. Or true negative is classifying the prediction that correctly classifies a data point in another class, which will be called a class negative class. So we classify them in a different class. False positive is the classification prediction that incorrectly classifies a data point in one class, which we will call the positive class. So when we actually select something into a different class, or false negative is the classification prediction that incorrectly classifies a data point in another class, which we will call the negative class. Right, so we'll actually see examples there to be able to see what it means. True positive. We choose what a positive class is. For example, let's say a cat is a positive class, then the negative class is not a cat. So in this case, we have a cat. The model predicts that it's a class cat, and this is a true positive. Why? Because it is a cat. And then here's a true negative. We choose that the positive class is, for example, we choose what a positive class is. For example, let's say the cat is a positive class. Then the negative class is not a cat. For example, we have a dog and we put it into the model and predicts that it's not a cat. So in this case, we have successfully predicted that it's not a cat. So this is a true negative, which is we have chosen correctly that it's not a cat. Now here's a false negative, is when we have a cat, we put in the model and it chooses that it's not a cat. So this is a what we call a false negative. It's supposed to be true. a true positive, but it's instead a false negative. It's not a correct negative. And then similarly, a false positive is when we have a dog put into the model and classified as a cat. This is a false positive because remember the positive is the cat and negative is not a cat. So in this case, we have a false positive. It's a false cat. That's practically what it means. So here we can see a diagram where we break down these four concepts, right? We're going to send the true, false, positive, and negative. So if we choose, if this is a true positive, then we have a cat and we predicted a cat. If this is a false positive, then we have a dog and predicted a cat. If this is a false negative, we have a cat and we predicted another cat. If we have a true negative, we have a dog and we predicted another cat. So you can see that at the two diagonal lines in the left corner, top corner, and the right bottom corner, they're the correct ones. And we want to have many of those. So we want to have this true positive and we have this true negative. So the diagnoses are correct predictions. So we want to have a lot of these options. Okay, so we want to hope that these numbers are big. We don't want to have this, guys. We don't want to have false positive, false negative, because that will be incorrect predictions. So here is what we call this form of organizing this data is called the confusion matrix. So the confusion matrix is a table showing a number of correct and incorrect predictions for each class. And now here we're talking about a two-dimensional class, right? A binary class. It's either one or the other, but we can extend this to multi-classification. So just remember, this is just a binary class, but we can extend this to multiple classifications. So while the terms true, false, positive, negatives are used in classification, the emphasis here is understanding and interpreting a confusion matrix. Pay attention on how the predictions are organized. So here we have if it is a predicted values and the actual values. So if it is a predicted that it was yes and it's actually yes, we call that a true positive. If we predicted it was yes, but it was no, it was actually no, that was called a false positive. If we predicted no, but it was yes, that was a false negative. And then we have predicted no, but it was no, then it was a true negative. So that is the what we call the confusion matrix. Now we can extend this concept to multi label, right? For example, here we have on the left side a binary classification, but we can extend this to a multi classification. And in this case, we would have instead of saying, it's like having, instead of just having cat or not a cat, we could have cat and dog. So in this case, we just have two classifications. We want to determine if it's cat or dog. So in that case, it's either a cat. If we predicted a cat and it was a cat, then that's good. If we predicted a cat but it was a dog, then that's not good. It's a false negative. It's a true it's a false true. And so in this case, we would have actually count how many times we actually selected the apple correctly. So the actual on the left side and the predicted on the top. So the column will be the predicted and the row will be the actual. So we predicted an apple and it was an apple, the actual was an apple, then we have 10 of them, that's good. But if we predicted it was a grape and it was an apple, we want to count how many times we did that. If we predicted it was a banana, but it was an apple, we want to count how many we did that. If we predicted it was an orange, but it was an apple, we want to count those. And then if we predicted it was an apple, but it was a grape, we want to count those. If we predicted it was a grape and it was grapes, so then we want to count those, and so on, right? We want to be able to we want to make sure that our diagonal line is hopefully has a lot of values there, because that means that we have a better prediction. So now what we can do is talk about the hyperparameter tuning K. So trying many values of K to see which one is the best process is called hyperparameter tuning. So if we try K equals 1, remember, we're just going to look at one neighbor to determine what the label belongs to, what class the label belongs to. Now that's not going to be very efficient, right? The smaller the K, the more bias. the more underfitting would be this. So then we'll talk about that. So if we have k equals 5, this is gonna be give us probably a better prediction, right? Because it's gonna look at more neighbors than just one. If we have k equals 25, that might give us a little bit better, or might not, right? Maybe it's going to overfit our data. So to determine our hyperparameter, so in ML models have two types of variables, knobs that can be tuned to produce better predictions. So what are those two type of variables? So we can have the parameter or the hyperparameter. These values are determined by, so the parameter, the training algorithm, and the data. So the parameter will be by the training algorithm and the data, and the hyperparameter you're gonna you before training. So you're gonna determine what the hyperparameter will be before you actually do the training. So what will be the parameters in a linear regression? So the coefficients of your and the y-intercept on your linear regression would be your parameters. So depending on those parameters, we can actually change them to remember when we had that line. We started with the line, and we kept moving that line until we were able to find the sum with the smallest difference between the y values. So that was the parameters that the parameters allow us to be able to fix that line until we found the smallest sum. And KN does not have a parameter. And similar, the linear regression does not have a hyperparameter, but the KNN does have a hyperparameter, and that's what we're gonna be able to tune between. We can change it between 1, 3, 5, 7, 9, 11, so on and so on until we find the best one. So let's talk about bias and variance. So bias is much more is how much the algorithm has assumed before it even sees the data, and that kind of follows into the same definition of bias, right? If you're trying to if you're meeting someone by the first time and you don't even know the person and you're already making assumptions about the person, then you're being biased, right? And that's not good. In other words, bias is how much the resulting model missed about the data because the algorithm did not think to even look at the certain way, right? So that's being biased. That's practically similar to how people are biased sometimes. Variance is how sensitive the algorithm is to a specific data it is given. In other words, variance is how much models vary when trained by the same algorithm but from the different data. So bias would not it's imagine that you have already predetermined how the data would look like without, or what the class where the label would be classified without even looking at the data. So it's already predetermined without even having the data. That's being biased. So you don't want to have a model that is too biased. And then you don't also want to have a class, or sorry, model that is too variance. Variance means that just by adding a little bit of data is making a big change in the prediction in the model. So we'll see a little bit in a better example to see the difference between those two. Bias and variance, a game of darts. The tension between small and large k is an example of the bias variance trade-off. So k will influence the bias in variance. We can think of the trade-off in terms of a game of darts. The goal is to hit the center of the circle showing to the right. Get the right prediction. The red X are each model's attempt to doing this. Okay, so if we have high bias, it means that is all over the place, right? That is already predetermined the value without even that is not very accurate to the prediction of the value. So it's already predetermined what the label class should be without even looking at the label. So it's going to be all over the place. High variance means that the numbers will be very So like I said, right, so high bias means that you're way off to the center of the target. High variance means that your points are very spread out apart. They're very far apart, meaning that your data is just by having changed a little bit of your features is going to drastically point to a different direction, to a different point very far away. So they're not gonna be close. They're not gonna be clustered together. So high variance, what it does, it spreads out the values. So the smaller the variance, the closer the points are to each other. That's what it means. High variance versus in low variance. Low variance means that the points will be closer together. High bias means that they're off from the center of the of the uh, of the target. So you can still have a low bias, but have a high variance where the points are very spread away from each other. And you can have a high bias and a low variance, so you can still have very far from the center, but they're very close to each other, right? So you're still not gonna be able to get the target that you wanted. So the ideal thing would be is to have a low bias, low variance value. Okay, so that's the goal. So small k relies heavily on the specific training data, meaning it could change widely with different training data. This is a high variance. So small k means high variance. Small k means high variance, meaning that, so remember what I said, right? That just by changing the data a little bit, you're gonna determine something different, right? Almost something different. So here, for example, you only have your k equals to 1, that is only gonna look at the closest neighbor. And you could be very close to multiple different classes, and if you're closer to one just by a little bit, then that's gonna automatically be a class A. If you're close to another one, that will be a class B. So it's overfitting, right? It's a high variance. It's varying a lot just by just having by having a k equal to 1. So that's gonna be an overfitting. Small k picks up on all the nuances of the data, meaning it will get a sense of the structure distinctly. So it's going to be a low bias. So small k means high variance, low bias. Small k implies low bias. Large K summarizes most of the data, meaning it is very consistent even when changing the training data. That is a low variance. So it's not going to vary much if you have a high K. So high bias means an underfitting. Large K ignores the difference between each data point and is vastly over generalizes this high bias. So having a large K is going to give you a high bias. Small K, small bias. Large K, high bias. So they're directly proportional to each other. So small k, small bias. Large k, large bias. So just to remember that. And high bias means an underfitting. So here's a summary between bias and variance. The tension between the small and the large k is an example of the bias variance trade-off. So if we have a small k, we're going to overfit. If we have a large k, we're going to underfit. Small k is going to be high, very dependent on each data point. Predictions will change widely with different training sets. So that, remember, that's small k. When we are looking at small number of neighbors, then it's not going to be well predicted to what the actual value is. And on the other side, having a large k on the variance is going to give you a low variance, unlikely to change predictions very much with the different data sets. Small k is going to give you a low bias, picking up on every nuance of the training data, unlikely to ignore anything. And a large k is going to give you a high bias, vastly overgeneralizing and ignoring most of the difference between individual data points. So remember that our goal is to have a low bias and a low variance. So our goal is to be able to determine a K. We need to be hyperparameter tuning to find a K that gives us a low bias and a low variance. Okay, so that's by changing the number of K. So that's practically we're gonna be doing to make sure that our model is the best one that we have. Now, how are we gonna do that? Now, remember that every single model will have the same steps. The first thing is to load in the data. Second step will be to decide which features will be the predictions on your kx values and which features will be your predict on the y values. We're gonna split the data into training and testing data sets, import the machine learning algorithm, set the model's parameters, fit the model on a training set, and test the model on the data set. Draw visualization if applicable to the model, evaluate the model performance, and apply your model. Right, so we're gonna set the model's parameters, so that could be your hyperparameter tuning. Okay, so that's when we talk about set the model's parameters. So again, step 1, step 2 would be collect raw data, prepare the data. Right, that's usually what takes 80% of the time to make sure that the data is clean and it would be ready to put into our data model. So we're going to load the data, decide which variables will be predictors and which variables will be the predict. Will predict. Split the data into training and testing set. Step 3 and 4 will be model selection and training model. So we're going to import the machine learning algorithm, set the model's parameters, fit the model on the training set, and test the model on the test data set. Draw visualization applicable in the model. Validate and improve model. So that'll be evaluate performance, and then also make the predictions to apply the model. So those are the 6 steps that we're gonna go over, that we're gonna keep doing over and over and over. So how are we gonna apply this into a KNN model? So we're gonna load the data just the way we did it before. We're gonna use datasets.load dataset name. So that's if we have a built-in data. In this case, sklearn database is going to have some data there, so we can do that. We're going to create a data frame. So we're going to use pandas data frame and use the dataset .data for our data, and columns will be our dataset.features _ names. Then we're going to determine which one will be our target, our label, right, column, which in this case, we're going to call it the target, or we can call it something else. And that will be the dataset.target. We're going to show or display our data frame, and then we're going to choose in step number 2, 3, we'll choose the features and split the data into the training and testing data sets. So what we're going to do here, again, we're going to use the model selection .training test split to be able to split the data into the X training, X test, Y train, and Y test. So we talked about this procedure in linear regression, so it's the same thing, right? So we're gonna pass in the features that we want to be used as our X training, and then we're gonna pass in our Y data value. So we're gonna pass in the data for our features, and then we're gonna pass in the data for our target. Then the test size determines how do we want to split up this data. So in this case, we're saying that we're going to split it up into a 80-20 size. So the test size would be 20% and the training size would be 80%. Now we're going to use a random state 42. You don't need to do this, but if you want to have somebody else to be able to simulate your results, you need to put a random state. So that's going to fix the random number, and you're going to have that whoever follows your procedures will contain the same results. Even though the data was random selected in the beginning, it is chosen to be a random. It is still gonna be attainable by other people. And then we can do shuffle true, so we can shuffle the data so it can be more random. And then we're gonna import the ML algorithm. So this up to before, everything was the same. Nothing changed from the linear regression. So now this is going to start changing here. So step number 4, we're going to import the machine learning algorithm. So we're going to do from sklearn.neighbors, we're going to import the the KNeighbors classifier. So we're going to import that KNeighbors classifier, and then in step number 5, we're going to initialize and set up our hyperparameters for our KNeighbors classifier. So in this case, remember in linear regression we didn't have to put anything inside that parentheses, but in this case we will have to put a number for our n neighbors. So our n neighbors is practically our k. Now again, we don't want to use a 4, an even number, we want to use an odd number. So just to remind you about that. And that will be our model. And then we want to yield to do a fit test and visualize if applicable, right? So now what we're going to do is we're going to fit our model based on our data. So we're going to use our model that we just created with the k value of 4. We're going to fit our data to the training, to the x training and the y training. And then now that our model has been fit, that it has been trained, right? Fit means train. So that's what it means. Now that it's trained, we're going to use our model to predict what the x test values would be. So we're going to plug in all the x tests and see if what does it predict. So that's going to be our pred. You may be wondering why is the x capitalized and why isn't, and the y isn't. And remember that we talked about that the x is think more as an array of multiple features. So that's why we want to emphasize that the way we emphasize that is by having it capitalized, while a y is only one column. So x is multiple columns, multiple features. So that's what it means, and then the y is only one column. Okay, that's why we have them different. It's not a typo. That's the way we tend to do it. X capital, y lowercase. And now if we want to be able to draw a visualization of our data, when building classifiers, it's often nice to visualize the position boundary. We can do this by plotting 2 dimensions of the data and coloring the background based on which class a new data point in the location will be classified as. So don't worry about this code, we have given it to you. So here we're using the more powerful plot, which is a subplot. So we're going to use the plt.subplot. We're going to determine the size of our plot to be 10 by 6. We're going to have the figure and the axle, and then we're going to do the next part will be to determine the colors of the background based on which class is the model would classify it as. So we're going to have we're going to use the mp downpy.mesh grid, and we're going to arrange our values. So we're going to use the numpy arrange. So we're going to have from 6 to 10, from 30 on a scale of 0.1 for part of your x values, and your y values will be ranging from 6 to 42 with a 0.01 separation unit. The z will be a model. We're gonna take our predictions between those 2 values. So we're creating those x's and y's, and xx and yy. So we're gonna predict whatever that value is. In our case, would have been predict and y test, but in this case we're using the mpc underscore xx dot label